Docker is incredibly successful. It started in 2013 and it has just taken off like wildfire. And so if you don't know Docker, you should probably start learning Docker. For our customers that don't know Docker, they should probably start learning Docker. It's a really big deal. Supposedly it's the #2 most popular open source project out there right now. There's lots of vendors that are participating in it, so not just IBM, and not just Docker for that matter, but also Red Hat, VMware, Google, Amazon, so forth and so on. There is a governance body set up around it so that Docker Corporation does not unilaterally control the Docker standard, and that's really important. We don't want any one company having unilateral control. We want we want to have a governance board, and this has that. And so Docker, containers in general and Docker specifically is a really big deal. Part of what we want to keep in mind is that Docker is not the only kind of container. So for example, Bluemix also supports Cloud Foundry, and Cloud Foundry uses Linux containers, but they're called Garden containers. They used to be called Warden. That was an old standard. Now the newer standard is Garden. And Garden containers are not Docker containers. They're both Linux containers, but Garden has gone off in a different direction. Compose uses Linux containers as their own kind of proprietary standard that they call capsules. And capsules are a kind of Linux container, but again, they are not Docker containers. So not all Linux containers are Docker containers, but nevertheless, Docker is really hugely popular, has really taken Linux containers and made them far more popular and far more widespread than they ever were before. And so a lot of times when people say containers, what they mean is Docker containers. As I describe it, I try to be specific, but every now and then I slip too. Docker's mission is to be able to take software and wrap it up as containers that you can run anywhere. And so they describe kind of the life cycle on this as build, ship, run. And if you're familiar with the 12-factor application approach to doing applications, they have one of the 12 factors is called build, release, run. This is very much the same idea. That you take your application and build it however you want to, and you build it into whatever runtime that it needs to run on and whatever operating system that needs to run on and so on. You build all that so that you have a fully running application. Then you wrap it up and package it as a container, and you ship that container. So that's creating a version. That's saying, all right, everything that we have up until now goes into this container image, and that's a version of our application. And then, and again, you can still track the source code separately and things like that. So you might have versions of the source code as well. But the container itself, the image, ends up being a version where you say that you know what version of the software is in it, as well as what version of the runtime and the OS and all that. You know that's in there. And then once you've packaged it as a container, you can then run it. Or let me put it this way, is once you package it as a container image, you can then run containers that are based on that image. And those containers, you know exactly what's in them because you know what image it came from. So by knowing what's in the image, then you know what's in the container. And that container, when you run it, you can run as many of them as you want, so you can get horizontal scalability out of this. And you can run it on any platform that you want, the whole portability thing. And so here's where they show that when you go to run, you can run any app. So kind of like we were talking about before, any software that you can package inside a container, then you can run in a container. And then once you've got that container, you can run it anywhere. So you can run it on any of these platforms, any of these different operating systems, any of these different virtual machines, virtualization standards, any of these different cloud platforms, your own laptop computer, your own desktop computer. So once you have this container image, you can run containers from it. And those containers, you can run and using those containers, you can run any software on any platform. That right there, in a nutshell, is sort of the value statement for Docker. These are the parts that go into Docker. Is you have the image, the container, the registry, which should really be called a repository. I'll keep coming back to that, and the Docker engine. So the image is a snapshot of what a container would look like when you start one. So it is read-only. It can't be changed. I don't know any way to go in there and change it. So, and it's very easy to share. So it's a big file, so to speak, in a lot of ways. And so as a big file, basically, I can give a copy of it to you. You can very easily receive a copy of it from me. And now we have the same thing because it's sort of like a big file. It's sort of like a zip file that it contains. It's a big file that contains a bunch of little files. There is, once you create an image, then from that you create containers, and containers are the actual runtime. So those are the things that are running that have business logic running in them, that are storing data and doing whatever else the process inside the container does. So the image is not actually running. The image is, if I wanted to run, here's what it would look like. The container is, okay, now I'm actually running. So the container starts off basically as being a copy of the image. It's an image that's expanded into a runtime environment to actually be able to run. And the beauty is you can create lots of different container instances off of the same image, and they're all equivalent. They're all identical. They're all just like each other because they were all created off the same image. And then you have the registry, and the most famous example is the Docker Hub. But also, when you install Docker locally on your machine, then part of what you're installing is your own private registry that's local to your machine. So basically, every place that you have a Docker runtime, part of that runtime is you have a registry. And the way you deploy stuff into your runtime is typically that you copy an image from some general shared place to your own local registry, and then from there you run containers off of the image that's the copy that is in your local registry. Docker Hub is sort of the mother of all registries. It's one that's hosted by Docker, and it's sort of the source of the Nile or the root of the tree for where all Docker images are stored. Now, the caveat there is, the good news is when you put an image into Docker Hub, then you can share it with the whole world. The bad news is when you put an image in Docker Hub, you're now sharing it with the whole world, which may not be what you want to do. So this is why you continue to have your own private registries, and why a lot of containers or a lot of images that you create, you'll probably never store in Docker Hub because you don't want to share them with the whole world. They're private to your company or your project, and you don't want anybody else using them, so then you don't put them in Docker Hub. But for stuff that you want to share with everybody, then you put in Docker Hub. So there's like empty Docker containers that simply have an OS like Ubuntu installed, so that's helpful. IBM takes WebSphere Liberty and wraps that up and packages in a Docker container and puts that in Docker Hub, along with a license that says you can only use this for development purposes. You can't use this for production purposes without buying a license. So there's all kinds of stuff that's up in there, but that's in the Docker Hub, but it's stuff that's intended to be shared. Now, Docker calls this a registry. I think that's wrong. It's actually a repository. The difference is the registry is kind of like the card catalog in a library. It's a list of what books it contains. The repository is the bookshelves that contain the books in a library. So if you lose the registry, you can recreate it again. It just takes a lot of time. You have to reindex the whole thing. If you lose a repository, all your data is gone. So even if you still have the registry, that doesn't help you very much. So Docker Hub and the Docker registry is actually a repository. It's not just a list of images, it's actually the data for the images. As you add more and more images to your registry grows a lot. It takes up a lot more disk space because it actually contains the data. So keep in mind that it really is a repository. And then there's the Docker engine. And what the Docker engine does is it runs containers. So images are stored in registries, and then when you say you want to run a container that's based on an image, you'll create a container that is a copy of the image, and then that container will run in the Docker engine. And the Docker engine is a thing that is implemented differently on a bunch of different platforms. Now take that with a grain of salt, because in the end, the Docker engine really only runs in Linux. And so any other platform that you run it on, if it's not a Linux platform, then that means it's doing some emulation to be able to run Linux on top of Windows or on top of Mac OS or something like that. In the Power world, Power Linux can run a Docker engine, but AIX cannot run a Docker engine. So in order to be able to run Docker on top of AIX, you have to do this emulation kind of thing, because it doesn't run natively in AIX, because AIX is not Linux, it's Unix. The engine you can think of as being a little bit like the hypervisor for VMs, or a little bit like the JVM for Java. It's the thing that converts between the standard container, which is the same on any platform, and how you actually run it on that particular platform. And so the engine is really key. That basically, when you say that an environment contains a Docker engine, then that means it runs Docker images and Docker containers. If it doesn't contain the Docker engine, then you got to worry about, well, so is this really a Docker container, or is it some other kind of container, or what is it? So the Docker engine is the most, of these four, it's the most fundamental part of the runtime. But basically, the image, the registry, and the engine are a triangle that form the runtime, and so that you can run a container. So the container is based on the image, which comes from the registry, and the container runs in the engine, and that's what actually runs your software. So it's almost inevitable when you get in this part of the conversation, you've got to compare VMs and containers. So let's do that kind of quick. These are standard images that come from the Docker docs, and this is kind of the standard way of explaining it. With a virtual machine, you may or may not have a host OS, which is running on the server. So that's the operating system that's running on the hardware. So if you're running a Mac, then that's the Mac OS. If you're running a Windows laptop, then that's Windows. So on top of that, you're running a hypervisor. So if it's a type 1 hypervisor, there is no host OS, but typically we're thinking this is a type 2 hypervisor, and so yeah, there's a host OS. And then the hypervisor is what runs VMs. It's what virtualizes the compute resources and makes them shareable. So you end up with virtual memory and virtual CPU, and it can be shared across machines that we call virtual machines. Each virtual machine runs its own guest OS. So here we show 3. So you can think of one of those as being Windows, another one as being Linux, another one as being Mac OS, which is a kind of Unix. So they might all 3 be the same operating system, or they might be 3 different ones. But in any case, they're definitely 3 different copies. If you patch one, the other 2 stay the same. They're 3 separate copies, and they're entire copies of the entire operating system. So this is part of what makes virtual machines kind of heavy. Then on top of that, you have all the libraries and binaries and runtime environments and middleware and stuff that you want to install on top of the guest OS to be able to make it do what you want to. So you want to install a Java environment, or some middleware like DB2 or MQ or something like that. And then on top of that is the application. So that is your Java code that's running in your Java environment. It is your data and your schema that's running in your database, things like that. So this is the typical stack. And what this shows is the whole stack above the hypervisor is the virtual machine. And the virtual machine is fairly big. By comparison, this is what containers tend to look like. Is with containers, you definitely have a host OS. And it's kind of funny that they like to call it a host OS, because it's kind of like Henry Ford said, it's any host OS you want as long as it's Linux. As far as I know, there's no way to run the Docker engine. There's no way to run Docker containers on top of something else. It's got to be Linux. Now, more specifically, it's not the entire Linux operating system. It's the Linux kernel. All that the Docker engine requires is the Linux kernel. So then on top of that, they don't really show it, but there's the Docker engine. And the Docker engine, really, for their purposes, they kind of think of it as being part of the kernel, or it is the kernel, or it goes alongside the kernel. So they don't really show it separately. But you can think of the Docker engine as being somewhat analogous to a hypervisor. But again, it's not virtualizing things as much because it's always Linux. And that Linux kernel is what all of the containers share. So all the container running processes in Linux, they don't all have their own Linux kernel. Instead, if they're all in the same engine, then they're all sharing the same kernel. So on top of the host operating system, again, is your binaries. So again, that's your Java runtime or your middleware product, as the case may be. And then on top of that, you have applications. And so again, the applications are the code that you wrote in Java or Node or whatever the case is, or it's the other stuff that you've done to customize your middleware to be able to use it. And so what you see is that this whole stack is a lot smaller. And a lot of the reason that it's a lot smaller is because the host OS is smaller because it's only the Linux kernel. It doesn't have to be an entire OS. And because there's no guest OS. That rather than a guest OS, all the containers are sharing the same Linux kernel. So some of these binary libs might be more operating system type packages on top of the kernel, but those are optional, and those are only there if the container needs them. And if the container needs them, then don't include them in that way. Part of the idea here, part of the challenge for people who build Docker containers, and there are people, this is their career, this is all they do all day long. The challenge for them is they try to make the container as small as possible. And containers really lend themselves to being able to do that. Whereas virtual machines, it's a lot harder to be able to do that. Virtual machines tend to just be bigger. So what we see here is everything above the host OS is the container. And so app A and A prime, those are both sharing a certain set of binaries. And then apps B and B prime, all four of those instances are sharing a different set of binaries. And this, again, is part of how Docker is really compact, is that when two different containers are sharing the same set of files, then Docker will just run them once. And so that takes up a lot less disk space, and it takes up a lot less memory, and helps you pack more Docker containers onto the same hardware. So what's shown here is there's 6 different containers, 2 instances of A and 4 instances of B. So here's another way of kind of looking at the same thing, is again, the kind of layered architecture that goes into Docker. Is that you have the file system, and it's a shared file system. They actually use something called copy on write, which means as long as they're using it read-only, they all share it. And if one of them decides to change it, then they get their own copy so that they can change it. Then on top of that is the base OS kernel, which again is kind of anything you want as long as it's a Linux kernel, which means it's always the Linux kernel. And then on top of that, you can have binaries that represent more OS features. So some of these, they want Fedora, which is one flavor of Linux. These others, they want Ubuntu, so that's a different flavor of Linux. And then on top of that, on Fedora, they've installed Tomcat, and then separately next to it, they've installed Liberty. So Fedora is running both of those. And App 1 apparently requires Tomcat, and App 2 apparently requires Liberty. Meanwhile, on the Ubuntu layer, they've installed Tomcat, and then both apps 3 and 4, they both require Tomcat, which requires Ubuntu. And so what you've got here is 4 containers shown across the top, 1, 2, 3, and 4, and running 4 different apps. And the main thing to notice here is that they're built in 3 layers, and there's nothing magic about the number 3. The reality is usually the number is more like 5 or 10 or 20. But the idea is that layers can be shared. And so by building layers, what that means is that when you need to download a container, you usually don't download the entire thing. You just, you only download the layers that you don't already have. And so that's usually a lot smaller. And likewise, when you run a container, you don't necessarily run the whole thing. You run the layers that you don't already have. So that means the first container that you run tends to take up a decent amount of memory. But the second and third may take up a lot less memory because those layers are already running. Depends on what's in the layers. It depends on how read-only they are and how well they can be shared. But in general, Docker goes out of its way to try to share these things. So why are customers interested in Docker containers? What is all the excitement about? First of all, it's critical to doing hybrid applications. The idea of hybrid is that not all of your stuff is running in one environment, that there's a bunch of different environments that may be distributed geographically, They may be different platforms. Some may be cloud, some may be not cloud, some may be public, some may be in your data center. And again, so this becomes, like we were talking about at the beginning, very hard to share all this stuff, very hard to support all these different platforms. Well, containers make it a lot easier to support all these different platforms. That as long as all these platforms support containers, and specifically Docker containers, then that means that once you develop a Docker container, you can run it all these different places, and you can run it in kind of whatever combination you want to. Containers tend to allow you to be more productive because it is very easy to build your own container, especially if you automate it. If you set up pipelines for doing continuous integration and continuous deployment, that automates building the container, and then that automates deploying the container, putting it, getting it started, making it run. And the idea is that you can do all this very separately. So if I'm working on a project and you're working on a different project, I can build a container separate from the container that you're building, and that way both of us get to work at our own pace. So if I'm ready to do a new build and you're not, then I go ahead. If you're ready to deploy into production and I'm not, then you can go ahead, because these containers provide you the ability to not really to do your build separately, that's for DevOps, but having done a build separately, to package it up and deploy it separately. And containers let you do that, and that helps you be a lot more productive. That software teams, when they first start using containers, probably their productivity goes down because they're climbing the learning curve. But the learning curve isn't that bad. And once they progress along it decently, then they get to where they're at least as productive as they were before. And before long, they're more productive than they were before. They're able to get more work done more easily, because containers just makes it easier to package up your stuff and deploy it safely and reliably, and not disturb other parts of the team, not disturb other things that are running on that platform already. Containers are cool, especially Docker containers, because they run very efficiently. Like we say, they're a lot lighter weight than VMs are. So you want to use VMs for kind of coarse grain granularity, and you want to use containers for finer granularity. And so you can pack a lot more containers on the same hardware, use it a lot more efficiently, whereas VMs might take anywhere from a minute to 15 minutes to start. Containers typically take less than a second to start, or maybe a few seconds, depending on what's in them. But they start a lot, any decently written container starts a lot faster than a decently written VM. You can shut them down more easily. You can shut them down more cleanly. So one way to look at them is really as lightweight VMs. That's not entirely true. There's a fair amount of differences between containers and VMs. But still, one way to look at it is that just like VMs make it easier to divide up a computer and be able to start and stop parts independently, well, containers are like that too, except much finer grained. And so you can start and stop pieces a lot more easily, a lot faster, and there's a lot more of them that you can do independently. And again, the whole app portability thing, that once you package something into a container, once you take a piece of software and package it into a container, especially a Docker container, you can then run it anywhere, or at least test it anywhere. And so this way you don't have to worry so much about, well, am I building this for a certain operating system, or I'm building this to run in a certain cloud, or whatever. It doesn't matter. That you're going to be able to run it in all of these different places, and it'll run pretty reliably. And once you get the kinks worked out, it'll run the same on one platform as it does on another platform. And so you don't have to worry about the platform so much. You can worry about the software that's going to go inside the container. It'll be the operations people who, that's the dev. The dev people are worried about what software is going inside the container. It's the operations people that'll worry about how to make it run properly on this platform versus another platform.